Hello, Mr. Fig back again for another week of physics. This week we're going to be looking at the refraction of light. What happens when light crosses a boundary from one material into another. We'll start, the first part of this lesson is on the index of refraction, so let's get to it. All right. First, recall that light is an electromagnetic wave. That is, it's a transverse wave that is made up of a vibrating electric field and a vibrating magnetic field. And again, we'll talk about electricity a little bit later on in the course. But it is that electric part that we're most interested in. Because matter is made up of atoms, and the outside of atoms are where the electrons are located, it's the electric part of the light field that tends to interact with the material around us. So consider a photon of light, a particle of light, which is really an electromagnetic wave. So it's a packet of energy that consists of an electric and magnetic part. As that particle of light interacts with an atom, it interacts with the electrons in the atom. And those electrons will change the properties of the light. In this case, changing it from blue light to green light. Now, how it does that, why it does that at an atomic level is very complicated. But we're going to be looking at it at our level, a macroscopic level. So let's take a look at a little bit of what happens when light goes from one material into another material. So here we have two materials. We have light moving from air. We have two materials. We have air and glass. And remember, a material that a wave travels through is known as a medium. Well, I'm going to construct a normal line. And notice my normal line now goes through the two materials from the air into the glass. And to start our discussion, let's consider a ray of light that is going straight along the normal line and goes in straight along the normal line, so it has no angle of incidence. Well, in the air has very little effect on the speed of light. In the air, the light is traveling at speed c, where c stands for the maximum speed of light, the maximum speed possible for anything, and that's 3 times 10 to the 8th meters per second. But going into the glass, the electrons in the glass are going to interact with that light and slow it down. So the velocity of light is going to be less than c, less than 3 times 10 to the 8th, once that light enters the glass. And that's going to change the properties of the light. So the part that gets transmitted is going to have a different wavelength, or effectively a different color. Now, but remember, when we first introduced our ray model, we made it clear that these rays are just a mathematical convenience. That a ray just shows us how the wave is moving, not what the wave actually is. So let's take a step back, and instead of looking at what's happening with rays of light, let's take a look at light as a wave itself. Okay, so let's take a look at what happens to a wave as it crosses through a boundary. Now, we noted before when we first started talking about waves, the frequency of a wave, that is the count of how many waves strikes the boundary per second, cannot change when crossing a boundary. You can't have more waves going in than come out on the other side. So here we have our light ray traveling from air to glass with a velocity of c. Now let's replace this ray with an actual wave. And here I've replaced the ray with a drawing of the wave as it travels from air striking the glass boundary. Now, regardless of the types of boundaries, the frequency, the count of how many waves are coming in per second cannot change going from air to glass. So that has to stay the same. But I know that the electrons in the glass atoms are going to cause the speed of light to slow down, that the transmitted wave isn't going to be moving at c any longer. Now, let's start with the fact that the frequency of light in the air must be equal to the frequency of the light in the glass, that the count of the waves cannot change. Well, I can use the speed of light equation to change these frequencies into something relating the velocity of the wave and the wavelength. So remember that the speed of a wave was simply equal to wavelength times frequency. So that means the frequency is equal to the speed of the wave divided by the wavelength. And we've used the wave equation before. So here in the air, the frequency would be equal to the speed of light, c, 3 times 10 to the 8th meters per second, divided by the wavelength of the light in the air. Where in the glass, the frequency is going to be the velocity of the light in the glass divided by the wavelength of the wave in the glass. So I basically have the same equation twice. But this frequency cannot change. That means the left side, the air side of the equation, has to be the same as the glass side, the right side of the equation. But if I'm making this velocity smaller, then in order for it not to change, the wavelength has to be smaller as well. And the wave is going to have to bunch up. And we saw this when we were talking about mechanical waves way back in February. So here, the incident wave is coming in. It slows down, and that causes a traffic jam. It causes the waves to stack up because the speed has decreased. If the speed decreases, the wavelength needs to decrease as well. And this wavelength in the glass is actually going to be smaller than the wavelength in the air. Well, this amount that light is slowed down in a medium is indicated by the medium's index of refraction. Now, this is an empirical thing. That is, there's no easy way to calculate from basic principles what the index of refraction is. We have to measure it. Well, when we do measure it, we define the index of refraction to be the ratio of the speed of light in vacuum, that's c, 3 times 10 to the 8th, divided by the velocity of light inside the material. So if this was the index of refraction for glass, this would be 3 times 10 to the 8th meters per second divided by whatever the velocity of light was in glass. If this was the index of refraction of diamond, this would be the speed of light in vacuum, 3 times 10 to the 8th meters per second, divided by whatever the speed of light in vacuum is. Now, it's not easy to measure the speed of light in a material. We're going to see that we have a mathematical way of determining these index of refractions, but that's actually going to be the next lesson. But what we want to note is, because nothing can travel faster than the speed of light in vacuum, that 3 times 10 to the 8th meters per second is the fastest anything can go, that means that this velocity on the bottom must always be smaller than c. That means that the index of refraction always must be bigger or equal to 1, because this bottom of the fraction can never be bigger than the top. The denominator is always going to be a smaller number than the numerator. So one way to check your work on these problems is you should always get an index of refraction larger or equal to the number 1. Well, let's take a look at some common index of refractions. The larger the index of refraction, the more light is slowed down. So if you have an index of refraction of 1, it means your light's not slowed down at all. You would have c over c. The light is traveling at 3 times 10 to the 8th meters per second. But as the index gets larger, it means the bottom of this fraction is getting smaller and the speed of light is decreasing in the material. Here are some common index of refractions for everyday materials. So first, let's talk about air. We call the index of refraction in air 1. That is, we say that there's no change to the speed of light from vacuum. That's a little bit of a fib. In reality, the index of refraction for air is 1.0003. But that means it has a very, very small slowing effect on the speed of light, because this number is just a tiny bit bigger than 1. But for the amount of sig figs that we usually do in a high school physics class, which is usually 3, this number rounded to 3 sig figs is just 1.00. So I can say that the index of refraction for air is 1, the same as for vacuum. As I go on, if I look at ice, well, ice has an index of refraction of 1.31, and water has an index of refraction of 1.33. You may think that's a little confusing at first, since ice and water are made out of the same molecule, H2O. But remember that ice, when it freezes, becomes less dense than water. So the atoms are less close together. So it makes sense that light would have a slightly easier time traveling through ice than it does water. Now, this is clear ice. Generally, when you pull ice out of your freezer, it appears opaque, appears whitish. That's not due to the ice. That's due to the fact that there's air trapped in the water coming out of your faucet. If you actually boil the water first to get the air out, your ice cubes will freeze crystal clear. It's a lot of work and most people don't want to go through it. So when you freeze ice, it is actually clear. The cloudiness in the ice is actually the air trapped in the water. Now, if I look at glass, well, there are different types of glass, but most glass has an index of refraction of about 1.5. A gemstone ruby will have an index of refraction about 1.54, and diamond has a very large index of refraction, 2.42. Now, I said previously that the larger the index of refraction, the slower the light is traveling. That means that the speed of light in air is fast. But as these indexes get larger, I am actually decreasing how fast light goes. That is, as the n increases, the speed of light decreases. So as n gets larger, the speed gets slower. Now, diamond is actually the most optically dense material that we know of. That is, diamond has the largest slowing effect on the speed of light, and 2.42 is a very large index of refraction as materials go. All right, well, let's take a little bit more look at these indexes. So the larger the index of refraction, the more the wavelength is reduced in the material. Again, here is my wave coming through air, and then it strikes glass. Because the speed decreases in glass, the wave bunches up, and I get a smaller wavelength. And we looked at the fact that the frequency in the air must match the frequency in the glass. And I can replace those frequencies by the velocity of the wave divided by the wavelength. And I get the relationship that c over the wavelength in the air will be equal to v, the velocity in the glass, divided by the wavelength in the glass. Well, I'm going to rearrange this equation a little bit to solve for the wavelength in the glass. If I rearrange this wavelength, glass comes over on this, the wavelength of the glass gets multiplied over the left, the wavelength of the air gets multiplied over the right. I end up with this relationship. The wavelength in the glass is equal to the wavelength in air times the velocity in the glass divided by c. Well, this is basically the opposite of what we said the index of refraction was. So let me replace this equation with 1 over n. And I see that the wavelength in glass is the same thing as the wavelength in air divided by the index of refraction for the glass. So that's a very handy rule to know. It's a handy shortcut. You could always get this result if you solve for the frequency on both sides of the boundary, but if you want a very quick way to find the new wavelength, remember this relationship. The wavelength in any material is equal to the wavelength in vacuum, or air, since air doesn't affect the properties of light very much, divided by the index of refraction of that material. That means if I know what the wavelength is in air and I know the index of refraction for the material, I can tell you what the wavelength of the light is inside that material. And that's a handy thing to know. What is the speed of light in diamond, where n is equal to 2.42? Let me change my pen color. That's something easier to see. I know that n is equal to the speed of light in vacuum divided by the speed of light v in the material. So I need to rearrange this for v in the diamond. So that means that n times v is going to be equal to c, or that v is going to be equal to c divided by n. That means the velocity in diamond is simply going to be equal to, well, that's going to be 3 times 10 to the 8th meters per second divided by 2.42. Or I get that the velocity is equal to 1.24 times 10 to the 8th meters per second. So all I did was I started with the index of refraction equation, that n equals c over v, and I rearranged it for v because v is the speed of light in the material. So it's pretty easy. What is the wavelength of green light in water? Well, if I knew the velocity in water, which I could find using this equation, I could find the frequency of the light both in air and in water. And by the way, if they don't specify where the light is coming from, you can assume air because that's where we live and usually where we would send the light from. So I could find the frequency in the glass, and I could find, the frequency in the water and the frequency in air. But this type of problem is much easier if you remember that shortcut, that the wavelength in any material n is equal to the wavelength in air or vacuum divided by the index of refraction. So if I want to know the wavelength in the water, all you need to do is take the wavelength in air, which is 550 nanometers, and divide by the index of refraction of the water, which is 1.33. And then what I'll find is in this light, as it enters the water, the wavelength will change to 414 nanometers. And there you go. Okay, easy. So this is another handy equation to know. The wavelength in any material is the wavelength in air divided by the index of refraction. Q3 is another application of this. The wavelength of light changes from 630 nanometers in air to 520 nanometers in material X. What is the index of refraction for material X? So again, I'm going to make note that the wavelength in material X is going to be equal to the wavelength in air divided by the index of refraction of material X. That index of refraction is what I'm looking for, so I'm going to solve for it. First, I'm going to multiply the n over to the other side. And then simply all I need to do is divide out the wavelength from in material X to find out what the index is. So the index of refraction will be the wavelength in air divided by the wavelength in material X. Or that's going to be 630 nanometers divided by 520 nanometers. So in this case, the index works out to be 1.21. Now, this is a good place to check your work. Remember that the index of refraction must always be larger or equal to 1 because the velocity must always slow down in a material. Here I get my index of refraction is 1.21. That is larger than 1. That means that the speed of light is slower in material X, so that makes sense. So that gives me confidence that I put my wavelengths in the right place. But notice none of these problems are very difficult. At this point, I would go try some of the practice problems, some of the homework problems this week on the website, and try these type of problems, and you should be able to get through them without too much difficulty. Remember to always write your equation first and rearrange. If you're the most likely spot you're going to make a mistake is if you confuse where the wavelength is what in what material. That is, read the question carefully. Make sure that you have the right wavelength for air and the right wavelength in the material before setting up the equations. The next lesson will be on how do we actually measure these index refractions and how do we know how much the light bends. And that is using an equation known as Snell's law, but that's the next lesson. Okay, see you then. Bye.